In this video, we'll begin to look at exponential functions. So now we're introducing a new class of functions called exponential functions. And these kind of follow a pattern exactly to their name, right? They follow an exponential pattern. They happen to model many real-world phenomena very well. So these exponential functions come into play a lot when we begin to look at applications in physics, in chemistry, the mathematics of finance. So we'll quickly motivate the idea of exponential functions. We'll look at two examples, then we'll give a definition for exponential functions. So first, what is an exponential function? So the pattern that we're looking at here follows, maybe we start with 2 to the 0, 2 to the 1, 2 to the 2, 2 to the third, 2 to the fourth, 2 to the fifth, etc. So if we're thinking about a function, we're talking about one variable changing, the independent variable, and then the dependent variable is the output. So that would be like the y. So if we're thinking of like a y equals f of x here, what is going to be our x in this pattern? It's going to be the exponent. So now we're looking at functions that look like y equals f of x equals 2 to the x. So the independent variable is now in the exponent as opposed to in the base. We've seen many functions like y equals x squared, where the independent variable is in the base. So now we're kind of flipping that, and we're looking at the independent variable in the exponent. So here, typically we refer to this number as the base, and our independent variable x, we say, is in the exponent or is the power. But this is kind of the important thing that you need to know here, that the number at the bottom is your base. So now we'll evaluate some exponential functions. For f of x equals 2 to the x, let's start with x equals 0. So 2 to the 0, we know that that's just 1. X equals 1, 2 to the first power is just 2, that's just our base. X equals 2, 2 squared gives us 4. Now, if x equals negative 1, we're kind of moving along the negative half of the x-axis. We have 2 to the negative 1. Remember, the negative 1 kind of flips our base, so now we're looking at the reciprocal. We have 1/2. And then if x equals negative 2, we have 2 to the negative 2, and that equals 1/4. And we'll look at f of x equals 1/2 to the x. So for 0, again, we have 1/2 to the 0, which gives us just 1. If we have x equals 1, 1/2 to the first power is 1/2. X equals 2, 1/2 squared equals 1/4. And now we'll go backwards for x equals negative 1, 1/2 to the negative 1 now gives us 2. And then if we have x equals negative 2, we have 1/2 to the negative 2, which equals 4. So you can see that these are obviously related. They kind of have differing patterns of increasing and decreasing depending on the SIGN, the sign of x. And when we look at exponential functions, we'll typically not look at exponential functions with a base of 0 or 1 or any number less than 0. If you think about what's happening with an exponential function for a base with 1, so let's suppose we had like g of x equals 1 to the x. 1 to any number is just 1, so this just equals 1, right? So it's just a horizontal line, which is why we typically exclude a base of 1 from the basis for an exponential function. If the base is 0, same kind of idea, and then if the base is less than 0, we have some funny behavior there that makes it difficult for it to be extremely useful. So we'll usually avoid that as well. So an exponential function. The exponential function with base a is defined for all reals as f of x equals a to the x, where a is greater than 0 and a does not equal 1. So it's important to note here that this is strictly greater than 0, does not equal 0, and a does not equal 1. In the next video, we will graph some exponential functions. We'll look at the domain and range so we can have a sense of what they look like.